Dear viewers, in polymers, there is another important category of material is rubber, or is called as elastomer. Elastomers are high polymers having elastic properties. Only when the polymer possesses elastic property, it can be called as an elastomer. So the elasticity of the rubber results from its long coiled polymer chain. Since it is having coiled structure, when we apply some stress, it gets elongated, that is giving elastic nature to that material. And this rubber is classified into two broad categories according to its source. One is natural rubber, the other one is synthetic rubber. Natural rubber is natural origin, synthetic rubber is man-made. First, let us concentrate on this natural rubber. Natural rubber is obtained from trees, the rubber tree, in the form of rubber latex. So the latex itself is not a polymer. So we are not getting polymer directly from the tree. So that latex is having a monomer isoprene. This is the structure of isoprene. The latex we are getting from the tree is a dispersion of isoprene. During the processing of the latex, which is obtained from the tree, the isoprene dispersion, there is a monomer isoprene present in the dispersion of the latex, undergoes polymerization, giving you the polymer, natural polymer. Actually, the tree does not contain any polymer directly. So the latex present in the tree undergoes polymerization during the processing, giving you the natural rubber. Let us see how it is undergoing polymerization. So the isoprene unit, this is isoprene, otherwise called as, it is 1,3 butadiene substituted derivative, that is 2-methyl 1,3 butadiene is the IUPAC is the name of this compound. So isoprene polymerizes to give polyisoprene. It is natural rubber. This natural rubber, although the repeating unit of the natural rubber is this one, when we see the actual geometry, that is, geometry differs. Because of the presence of double bond, there is a chance for geometrical isomerism. Here this natural rubber is having cis configuration. Let us see how that structure exists. So this is the repeating unit of natural rubber. When we see the actual geometry, it remains like this. It goes like this. So this is cis polyisoprene. Cis indicates the like groups are lying on the same side of the double bond, that is giving cis configuration to this polymer. So the natural rubber is cis polyisoprene. It is not present in polymer as it is in the rubber tree. It is in the form of rubber latex. Rubber latex contains dispersed unit of isoprene. During the processing, this isoprene undergoes polymerization, giving this polyisoprene. And there are two geometries possible with this polyisoprene, but the naturally occurring polymer is only cis polyisoprene. This is the structure of cis polyisoprene. So we have seen two broad classification under rubber. One is natural rubber that we finished. Next one is synthetic rubber. Synthetic rubber is having all the characteristic properties of a rubber, but it is man-made. Like our ordinary natural rubber, the synthetic rubber is also vulcanizable. We will see the meaning of vulcanization, mechanism of vulcanization later. Under synthetic rubber, we are going to see two synthetic rubbers. Both the rubbers are copolymers. So before going to this, let me explain what is copolymer. I am taking ethylene. Ethylene, when polymerized, we are getting polythene. This is a homopolymer. We are taking one monomer, polymerizes to give polythene. Whereas in the case of SBR, it is styrene butadiene rubber. In this, unlike our polythene, we are taking two monomers. One is styrene, another one is butadiene. It is the best example for copolymer, and this copolymer is showing the property of rubber due to its elastic nature. When you are seeing this SBR, styrene butadiene rubber, we are not taking the styrene monomer and butadiene monomer in the same ratio. They are taken in different ratio. That is, they have taken 75% by weight of butadiene and 25% by weight of styrene. This mixture is taken and copolymerized. We are getting styrene butadiene rubber. Butadiene structure is already we have seen similar to isoprene. Only one thing, there is no methyl substituent. Here we had methyl in the earlier case. Here there is no methyl. This is butadiene plus styrene. Styrene is otherwise called as vinyl benzene. This is styrene and this is butadiene. These two on polymerization, copolymerization, giving you a copolymer, that is styrene butadiene. SBR, styrene butadiene rubber, it is a copolymer. And this synthetic rubber, as I mentioned earlier, it is having elastic property, it can be vulcanized. And for vulcanization, we are going to use sulfur. This SBR requires less sulfur requirement for vulcanization, and when you are comparing this with natural rubber, it is having some better characteristic properties. That and all we see later. So the second synthetic rubber is butyl rubber. So under synthetic rubber we have two rubbers, one is SBR and the other one is butyl rubber. So this butyl rubber is again copolymer like styrene butadiene. Styrene butadiene is a copolymer of butadiene and styrene with a different molar ratio. Butyl rubber is made by taking isobutylene with small amount of isoprene. So isoprene is taken in very small amount. The major portion is isobutylene. So this mixture of isobutylene having traces of isoprene and copolymerization giving you butyl rubber. That's all about natural and synthetic polymer. Next, let us move to the vulcanization of rubber. For rubber, let it be natural or synthetic, the rubbers are not meeting out our industrial requirements. So before that rubber is taken for making any article, it has to be given some treatment. So what type of requirements we are expecting from that material are some of them. I am listing out here. But the natural rubber and synthetic rubber, they are having some defects. The first one is they are easily affected by oxidizing agent. and they have low durability. If you make any material with this unprocessed rubber, raw rubber, the durability of the material is very less, and it is not having that much high tensile strength. For any rubber, the tensile strength and mechanical strength are important. But the raw rubber is having very low tensile strength, and thereby the material article which we are making with that rubber will have low durability. And normally materials will absorb water. This raw rubber is having very high water absorption capacity possess. So it is not good for a material. If it is absorbing more and more water, then the strength of the material will go. Our raw rubber is having very high water absorption capacity. And raw rubber undergoes elongation to greater extent. That is roughly about 1200% it elongates. So when it is getting elongated to that extent, it may not regain its original position, so the shape of the material lasts. That is higher deformation. The shape of the material is not permanent. So in order to avoid all these defects which we are focusing with our raw rubber, let it be natural rubber or synthetic rubber, that is taken for an wonderful technique called vulcanization. It is very simple. Vulcanization is nothing but compounding the rubber by heating it with hydrogen sulfide or sulfur or benzoyl chloride is called as vulcanization. So vulcanization is nothing but compounding the raw rubber with hydrogen sulfide, benzoyl chloride or sulfur is called vulcanization. So when a material is taken for vulcanization, all these defects are rectified. And in vulcanization mostly we are using sulfur to get better characteristic properties. So the sulfur vulcanization is nothing but heating the rubber with the sulfur at a temperature range of 100 to 140 degrees Celsius is called vulcanization. So vulcanization is done to get some better characteristics with the natural rubber and synthetic rubber, nothing but compounding the raw rubber with hydrogen sulfide, benzoyl chloride or sulfur. Mainly we are using sulfur as a vulcanizing agent. Here the sulfur is heated with rubber at a temperature range of 100 to 140 degrees Celsius, and we are getting the rubber with desired characteristic properties. So you may be wondering how this sulfur is giving all better characteristic properties. Now let us see that with the mechanism. So here is one polymer chain. The chain goes, and there is another polymer chain adjacent chain. When this is heated with the sulfur which we added reacting chemically with this double bond and introducing a cross link between the chains. So normally that natural rubber, let me say I want to make a ball using natural rubber. I am making an object like this. when it is kept on the table for some time, the shape does not remain permanent, it gets deformed. Because the chain, because of the stress, the chain slips one over the other, so the geometry or the shape does not remain permanent. Whereas once you are heating it with the sulfur is forming a bridge, forming a cross link between the two adjacent chains. Similarly here, for the sake of clarity I have taken like this, even the sulfide linkage may present between this and this and another chain, and this and some other chain, like that it may go in an infinite extent. See, that structure of that vulcanized rubber remain like this. So between these two, sulfur is, so the sulfur linkage called as sulfide linkage, sulfur cross link, is tying the chains together so that the material is not undergoing any deformation, mechanical strength increases, water absorption ability decreases, elongation, rate of elongation decreases. Here the elongation is more because the chain can move, but here the chains are tied down with one over the other, so that elongation is very much reduced. Now let me compare the raw rubber with vulcanized rubber in terms of the properties. It is very simple. Already we have listed out some of the problems which you are facing with raw rubber. All the problems are rectified. So the raw rubber, here this is vulcanized rubber. So already we have seen series of problems with raw rubber. Let me see, they are getting rectified one by one. First one is easily affected by oxidizing agents. Here that vulcanized rubber is not easily attacked or affected by oxidizing agents. So in raw rubber we had double bond. Double bonds are susceptible to the attack of oxidizing agents, whereas in vulcanized rubber there is no double bond, or double bonds are almost converted into single bond with the help of sulfur, so it is not easily affected by oxidizing agents. And second one is tensile strength. It is low, here high tensile strength. And low durability. That means if you make any object using this raw rubber, its life is very less, whereas here high durability. Water absorption is high in this case. Water absorption is very minimum in the case of vulcanized rubber. Elongation is very high, very low elongation. So these are the advantageous things we have with vulcanized rubber. Polymeric materials are widely used to get variety of particles, and according to the nature of the object we want to make, we have to modify the properties of the material. Either virgin polymer may be directly used, or the polymer may be, that is rubber, may be compounded with some other material. Here the rubber is compounded with some materials which is called as composite. So composite is a multi-phase material consisting a mixture of two or more macro constituents which are mutually insoluble. That means one constituent is not solubilizing the other. differing in form and composition. So here there is no chemical interaction taking place between the constituents of the composite. So they physically present in that bulk, and between the constituents there is a strong physical force operating which is giving the strength to that composite. So if you want to make a composite, we need two important things. One is matrix. So the matrix is a material which is going to hold the entire material, that is called matrix phase. Continuous body constituent which encloses the composite. So that is the medium on which everything is going to remain. That may be a metal, ceramic or polymer. If it is metal matrix composite, MMC. Ceramic matrix composite, CMC, and polymer matrix composite, PMC. Our consideration is only on the third category, polymer matrix phase. So here the matrix is made up of our polymer. In that we have dispersed several constituents which are going to give structure to that composite. So that is a dispersed, that is in matrix this is dispersed. So structural constituents, structure of composites, that may be a fiber or particulate matters, flakes, small sheet like material, viscous, are making this. So these are the two constituents of our composite. Here we have variety of composites. So the types of composite of our PMC, that is polymer matrix composite, is important. Anyhow, our concentration is only on the third one. Let us see one by one. Types of composite. The first one is fiber reinforced plastic composite. Fiber reinforced plastic composite. And second one is metal matrix composite. And third one is ceramic matrix composite. Our consideration is only on the first, fiber reinforced composite. Fiber reinforced composite is having three components. One is the filament, and other one is polymer matrix. That is, on this polymer matrix only the filament is going to be dispersed. So this filament is our dispersed phase, and polymer is the matrix phase. So that polymer is only holding this filament, and these two are binded together using a bonding agent. So just by combining these two, the strength may not be to the required level. So we are adding something called reinforcing agent, which are increasing the strength of the composite. That may be glass or graphite or alumina or carbon or boron. Like that, these materials are added not only as a reinforcing agent to increase the size as well we are. So they are added for a dual purpose, to increase the strength as well as a filler. We are adding these components. Fiber reinforced plastic matrix is made under various headings according to the nature of the resin matrix we are using. So in fiber reinforced plastic, the main thing is matrix, which is going to hold all other phases. So that matrix may be made up of polyester or epoxy resin or silicone resin, phenolic resin, and some of the thermoplastics like our PVC and other things can also be used. And the advantageous properties are, if when we are preferring polyester and epoxy resin as a matrix, they have very good mechanical strength. Especially the shirt button and others are made up of mainly with this polyester, and it is giving good mechanical strength, it is having very good shelf life, or wear and tear is very much better. And silicones, so the silicone rubbers are well known for its insulating property. When we are using silicone as a matrix, it is showing excellent thermal and electrical insulating property. They are very much increased. And phenolic resin, so the advantage of using phenol as a resin matrix is its property. It is having one property at room temperature. The same properties retain even when we heat the material to elevated temperature. That means no thermal degradation occurs, or there is no change in property at elevated temperature. And thermoplastic, so this thermoplastic is differing from other things because the repeatability and repairability. So in all the places we cannot use polyester or epoxy or silicone or phenolic. In few places we need to use thermoplastic as a matrix, so the repairability and repeatability are better with this. So these are the some of the types of fiber reinforced plastics where we are using the reinforced material as a glass, carbon, boron and aramid. On that basis they are reinforced. I told earlier, reinforcing is nothing but increase the strength. And fiber reinforced plastic composite having glass as a reinforcing material is having low density and corrosion resistant and high tensile strength. Because of this, they are used to make automobile parts, pipes, storage tanks. That is very important thing for storage tank because it's not undergo any corrosion. For that we are mainly preferring this glass fiber reinforced plastic because of its lightness. It is used for making pipes and automobile parts as well. And carbon fiber reinforced, actually it is having good lot of application. It is again, carbon is light, so the properties are similar to earlier: low density, corrosion resistant, high tensile strength, and the important thing we have is properties unchanged at elevated temperature. That means for high temperature applications this carbon FRP is widely used. And here structural components of aircraft because of its low density and strength, and helicopters and solar panels are made out of this carbon FRP. And the third one is boron reinforced FRP. It is excellent compressive strength and stiffness. That's a compressive strength. When we are able to compress a material, the strength can be increased further, and thereby because of the high strength it is used to make tail parts in aeroplane, because the horizontal and vertical parts of aeroplane is very important. So for that we are using this boron reinforced FRP. And aramid, so aramid means mainly it is a nylon related compound, that is a polyamide related substance is added here. Because of that nylon presence, its property is like metal like ductile property, that is the properties of metal, ductile, malleable and ductile. So ductility is more with this aramid FRP, and thereby structural components in aircraft, helicopter parts, rotor blades all are made out of this. Such an interesting material is our FRP.